Hey, so the topic of nuclear power is a pretty long one, so I'm going to split this into two videos. The first being sort of how nuclear power works, and then we'll talk a little bit about some international stuff and whatnot. So, nuclear power, when we say nuclear, we mean having to do with the energy that is holding together the nucleus of an atom. This is a potential source of energy, and one thing we'll see is that when certain types of atoms break apart, that releases some of the energy. If you're interested in fusion, you need to study some astrophysics. So fission is really what we care about. While there are multiple types of isotopes and elements that undergo radioactive decay, we really mainly use uranium, and particularly its isotope 235, to give us energy. In order to sort of kickstart that reaction, rather than waiting for it to happen naturally, we can bombard one atom of U-235 with a neutron, which makes it undergo fission, and the result is we get three neutrons that come out. We get some what are called fission fragments, so smaller atoms. It could be things like barium and krypton, those are pretty common. And then we also get gamma, that's the Greek letter gamma radiation. This is the energy that we capture. So when we do that, what's important is that because there are neutrons coming out of it, these neutrons can then go bump into another atom of 235 and we get a chain reaction. So if you want a visualization of what that looks like, here we have our neutron that comes and bumps into an atom, releasing energy. And then we've got these fission fragments and the neutrons that come out as well, and those can go and bump into additional atoms, nuclei, additional atoms releasing more energy. And so as this process keeps going, we have a chain reaction causing it to continue. Okay, so things you need to know is that uranium is not all composed of that isotope 235, and most of the uranium is in an isotope that's much more stable. It's uranium 238. Only a small portion of naturally occurring uranium, if you were to take a rock of uranium, remember it's a solid material, mostly uranium oxide, there would be a couple of atoms within that, but only about 0.7%. And we say that this stuff, because it undergoes radioactive decay and gives us energy, we call that being fissile. So if we wanted to have a chain reaction taking place, and a good probability that a neutron would actually bump into an atom of 235, we need to have a greater concentration of that 235. The concentration necessary is referred to as its critical mass. So in order to increase the concentration of something, you can either add more of the desired material, which is kind of impossible, right? You have a rock, or you can get rid of the undesirable material. And so what we do is a process called enrichment, where we're basically using particular instruments that would separate out the slightly heavier on molecular atomic level 238 from the slightly atomically lighter 235. And so that can be done in a couple of different types of materials, but basically if you want sort of a visual of that, it's like we're sort of shaving off some of the non-fissile material, and we get a smaller ultimate quantity, but a more highly concentrated in terms of the fissile material that we want. And this enrichment process is really sort of the point in the process that's really, really hard to overcome. So when countries are trying to develop nuclear technologies, this is really the sticking point, this whole how do we separate out, how do we enrich uranium? Okay, so let's take a look at what a nuclear power plant is going to be like. This is obviously a schematic, not a real thing. In general, in a power plant, we are taking liquid water and heating it up in order to turn it into steam, which turns a turbine, right? And that gives us electricity. In a nuclear power plant, the way we do that is we've got uranium, which is referred to as fuel rods. They're actually little sticks of this uranium fluoride. And as that is allowed to undergo fission, energy is released into this chamber, and we have liquid, mostly water, that's going from this chamber into the chamber where the water is being turned into steam. So this liquid never really comes into contact with the water that's being turned into a steam to turn a turbine. And then that liquid is ultimately cooled down by a whole separate set of water. And so that 3 different pipe systems helps prevent any of the potentially radioactive material from getting out into the environment. Additionally, the reaction takes place inside of one unit, and that is contained within another, and then there's often multiple layers of containment to prevent any radioactive gases from getting into the environment. Okay, so there are a lot of layers of protection to avoid catastrophic failure, because while this chance of problem is very, very low, when you do have a problem in a nuclear power plant, the results are really terrible. So one thing to think about is the same process of fission. When it's going uncontrolled, that we call that a bomb, right? We don't want that, especially if we're trying to make electricity out of all of this. So basically what we want to do is control the speed at which, or the rate at which, the neutrons are bumping into U-235. Because if you allow that to continually happen, but at a slower rate than normal, then you can sort of control the amount of energy that's being produced. And we do that in 2 different ways. One is that we have control rods, which are usually composed of boron. So if we were to sort of imagine this, we've got the fuel rods of uranium, and as fission is taking place inside there, they're sending neutrons off, and those neutrons can stay within the individual fuel rods, or they could go between the fuel rods. So to make sure that things are not going any faster than we want, we have these control rods that we can raise up to allow more reactions to take place, or we can lower them down so that less reaction is taking place within this moderator. And that's very important because, like combustion power plant, we could increase the amount of electricity being produced if there's increased demand, and we can also decrease the amount of electricity being produced as there's less demand. I mentioned the word moderator. So this reaction is taking place in a water bath, and that water acts as a moderator, meaning it helps to absorb the energy and prevent things from getting too hot too fast, which is really important because we saw in the 1980s the explosion at the Chernobyl nuclear power plant occurred because things got too hot too fast. It wasn't moderated enough. And in Fukushima, we saw that an earthquake followed by a tsunami damaged the cooling components, and so they had to pump seawater in to keep the temperatures low enough and not allow overheating. And then seawater was also escaping, and so there was some concern about radioactive iodine that got into the oceans because they were using seawater to prevent the kind of explosion that people saw in Chernobyl. So what do we do with our nuclear waste? Well, what do I mean by nuclear waste? After you have used your uranium long enough that enough fission reactions have taken place, radioactive decay has happened, and we no longer have this critical mass, we can't rely on that fuel to give us energy at a constant rate. And so we call that having spent fuel. But there's still U-235 in there. It's just below critical mass. So we have to keep it at first in an environment that's wet that will absorb the energy that is being produced as the rest of the 235 is undergoing decay. But that's a very, very, very long process, very slow. And so even after a while the process will give off very little energy, it still can give off energy. And so eventually that fuel will be giving off energy less frequently and less strongly. And so we put the spent fuel into these dry containment, which are composed of steel and concrete that sort of absorb the energy and prevent it from getting to the environment. Right now, in the United States, spent fuel is housed for the most part at the nuclear power plants themselves. We're trying to figure out what to do with it in the long term because, like I said, we're going to have radioactive waste for tens of thousands of years. And so there are different options, some of them more realistic, some of them less realistic. In the United States, we were planning to make a single repository. This is called the Yucca Mountain Repository. It's in Nevada. It was actually built, but political support for that changed. And so instead of being in support of it, the residents of Nevada no longer want to have the nation's nuclear waste in their state. And so it's not being used at all. And that's a concern because we don't know what to do long term. And then finally, I just wanted to sort of give you a sense of what this process looks like. So remember, uranium is a mineral that is mined. So we have the mining operation here, most of it as uranium oxide, and that gets converted into uranium fluoride. That's easier for us to work with in terms of the enrichment process. So we have a facility for enrichment, and then once the fuel rods are created, then those are sent to reactors, and after the fuel has been used long enough and is considered spent, it's either stored there or, depending on the region, it might be stored in a temporary facility, ideally, or the plan was for it to be stored long-term in geologic reserves, but as we said, that hasn't really happened. This is sort of a one-way trip, but there are places in the world where spent fuel is not treated as the end. It is actually sent back for reprocessing and re-enrichment. And so this is something where countries like France, where it's a lot smaller and the transportation distances aren't as big of a concern, they have been re-enriching their fuel since the 70s and are only now starting to get to the point where re-enrichment is no longer an option. Whereas in the United States, we really don't feel like we want to be transporting even spent fuel, the kinds of distances we have to worry about. And so we have very much a unidirectional process. So anything that's spent does not get sent back for re-enrichment.